it's just common knowledge. Like, carbon is bad for the atmosphere, oxygen good, trees good.
4 for 3, like all that.
Yeah, like,
Alrighty guys, good afternoon.
Humans are
Welcome
powerful.
back. If you have notes on refraction, Snell's law, things like that, I'll take them right now.
This one's honestly, the pause for this one
Got a
kind
little
of
issue with the quiz.
Issue with the quiz.
If you finish the pods during class, you get extra credit. I'm do like most of it at home and then finish it in class.
You know what I used to do last year? Question? Odds? I used to just used to never check.
Oh really?
He just used to check that you uploaded something, and then he'll give you a hundred.
Reminds me of this guy.
Yeah.
You would not check your actual. You could turn in the same notes you turned in last.
Well, it depends like who it was. Like certain people she would know lies, or like she would like actually. I'll send you a picture.
Not correct. I don't know where that picture. The picture that's in the quiz that is definitely not a PDF of the quiz.
Look at the quiz.
Well,
It's somebody's driver's license. Warm, wait, because there's somebody have their ID with them.
Go back.
Korma? You can see your address, gang.
re-upload the quiz again.
How did he even get this?
I guess from if you guys all the senior stuff, you probably need to submit your driver's license for some like for all the senior events and stuff.
Oh yeah.
Your ID.
It's Ashley's. You know this person?
That's probably from last year. No, it's not in a day. It's like over. That's what I was saying. You have to do it over the course of 18 months. 18 months.
Minimum.
So do I have to do one thing for every aspect: creativity, activity, service?
I mean, yeah, but it doesn't have to be like a specific amount.
Alright, our dad joke for today.
Any of a cast project.
How does Darth Vader keep his Star Destroyer warm? How does Darth Vader keep his Star Destroyer warm?
Forces it to?
With a space heater.
The space.
Alright, yes.
Specifically in extra space.
Alright guys, so we are moving on and upward. We're talking about refraction today, so lots of cool stuff to talk about. There was no quiz last class. There will be a quiz for today. I just have to re-upload it because I don't know what happened with that picture. Yeah. So, let's go ahead and get started. Please get out your IBE equation sheets. You take a look. Because we've got multiple equations to talk about today. Yes. So we are in the C3 to be precise. So after A and after B, but before we get to D. Okay, so notice also, so if you look on page 10 down here of the IB equation sheet, we've got some C1, 2, 3, and 5 for the standard and the higher level. But then there's more additional higher level stuff for C1, C3, and C5. Okay, so There will be some things, not today, but maybe sometime soon, that we may have an HL only day, but I'll let you guys know. And of course, it'll be on the homework schedule when we actually get there. But just so you guys know, there are some wave stuff that are, that's HL stuff only, but everybody needs to know this stuff for today. Okay, so we are looking at Snell's law here. So at the top of the C3, we've got our Snell's law, but what we don't have actually is the definition of the index of refraction, which is kind of weird. Like, I thought that it would actually be on here, but it's actually not. So just in case you need to know it by heart, then we should definitely practice doing that index of refraction. So we're talking about now, when we say index of refraction, we're usually talking about transparent things like glass or plastic or, you know, air or, you know, some sort of clear stone that light can easily pass through. We're not talking about opaque objects where light cannot pass through, that would not have an index of refraction because light doesn't pass through. Okay, so we're just talking about things that transmit light. When we look at this index of refraction, this n, and this is always going to be a ratio between the speed of light in a vacuum, c, divided by the speed of light in the substance. So if you look at a chart, and there should be a little chart in your books. Let me check real quick here. On page 360 something. Yes. Okay. So on page 359, they have a very, very small chart of indices of refraction and the relative speed of light. So you can tell that all of our indices are 1 or higher, okay? Which means that this fraction is always going to be at least 1, if not higher than 1. It's never going to be less than 1, because the speed of light in the substance is actually going to be less than the speed of light in a vacuum. So we can plug that speed in, we can calculate what the index of refraction is, and that index of refraction we use in our Snell's law, which is the next equation. So we've got our n1 over n2 is equal to sine angle 2 over sine angle 1. So pay attention to the order that they come in, but again, it's just on your equation sheet. You just got to make sure to copy it properly. Fun? No. Put the cards away. You should be preparing for your IA or studying HL stuff or something like that, but we're not playing in class. And then the last one is going to be the fraction of V2 over V1. So Snell's law could be applied to light, and we'll do lots of problems with light, but we also can apply it to like waves in the water. Okay, so if you read or watched, you should have seen them talking about waves in the water. As they go from shallow to deep water, they are going to refract, they're going to bend as well. But the reason why they refract or bend is because the waves actually slow down or speed up as a result of the change of medium. Remember, we talked about before that the speed of the waves depends on the medium. Okay, so if we're talking about waves in the water, if something in the water changes, like the depth, how deep the water is, then that's going to change the wave speed. Also, if it comes into like a section of warmer or colder water, that'll also make it refract. If you have like we have the St. Johns River coming in and it flows into the Atlantic Ocean. So then there's a change in salinity where you've got kind of fresh water meeting salt water. So waves that go from one to the other, those are going to refract as well. So if we change the properties of the medium itself, we're changing the speed, and waves that go from one to the other are going to refract. They're going to change their speed, and we can kind of see that we can use this right side of the equation for anything like the water waves, okay? Because we're talking about the speed of those waves and the angle of those waves as they come in and exit the boundary, which is really what we're talking about. We're talking about how do waves act at the boundary between one thing and the next thing, which kind of connects to last class we briefly talked about, or you saw in your books, that if we send waves on a string and we go from like a light string to a heavy string, then it's going to partially reflect and partially transmit, and based on the nature, if we're going from lighter to heavier or heavier to lighter, then the nature of those waves that are reflected are either upright or inverted. So kind of the same thing happens, but on a slightly different scale. So there are some really, really good pictures in your book on page 358 about the refraction of the water waves. And yes, it's cool to see those lines, but we're really going to focus in on those rays, because that's how we're going to measure our angles, okay? So we mentioned it last class with the law of reflection, but we're going to do use it a whole lot more when we're talking about, we've got our boundary and we've got the normal to the surface. The angles are always measured with respect to the normal, not with respect to the surface. So if we look at these rays, and these could be rays associated with the water waves or actual light rays, as we see refraction with light as it passes from like air to plastic or to water or something like that. So as we see these rays come in, it's got two ways that it can change. It can either bend towards the normal, where the angle 2 is less than angle 1, so that's going to be bend towards our normal, or it can bend away from our normal. It just depends on which one is the lighter or heavier substance. If we're specifically talking about transparent media, things that we can see through, we have the indices of refraction to help us. In this particular case, we've got the first substance N1, we've got our second substance N2. Again, this is where light comes from, like let's say the air, and it's shining onto a piece of glass or plastic or diamond or water or whatever it is. So in this particular case, this is so that our N1 is less than N2. So you have this concept happening here where as our light comes into our boundary, as it goes from a lower index of refraction, because we can assume that the index of refraction of air is basically 1. It's actually like 1.000 something else, okay? But still, within 4 sig figs, it's basically just 1, okay? So it doesn't change a whole lot as it goes from space to air, but it does refract. In fact, a result of the refraction of light as light travels from empty space into our atmosphere actually allows our number of hours of daylight to actually be longer than it should be. Okay, and here's why. We zoom out. Okay, so here's the Earth, and here's the atmosphere. It's not actually drawn to scale, because the thickness of the atmosphere is very, very, very thin compared to the size of the Earth, but not drawn to scale. So here's our sun, okay, and so the sunlight is going to go towards the Earth, okay, and as it reaches this boundary, assuming that it's a hard boundary, it's actually not. So there's like a gradual bending of this light because the air is more dense at the bottom, close to the surface level, and less dense at the top. So it's not a hard bend, but it's a gradual bend. but for the sake of explaining what's happening here, this light is going to bend. Actually, it's more like if we send it like this way, because as the Earth spins that direction, here's where we are, and we are approaching dawn. So it's going to be spinning this way, and dawn is approaching. So like 6:30 a.m. or something like that. So what happens is this light coming from the sun gets a little bent. Okay, so what actually happens is we see bent rays, and when we see the sunrise, okay, we are assuming that that light is traveling in a straight line. It's actually not, because it's bending, okay? But where we think the sun is there in space. So we actually get more sunlight than we should because the light is bending as it's going from the empty space into the Earth's atmosphere. So that's why, as we are approaching the fall solstice? No, fall equinox. Yeah. So the first day of fall and the first day of spring is usually when we should have equal amounts of daylight and nighttime. But even then, that's actually not true, okay? Because we always have more daylight because of the refraction of light coming from space into our atmosphere. So our days are naturally longer. We have more daylight than we actually should. Okay, now if we went to the moon and we experienced the same thing, because the moon doesn't have an atmosphere, our days on the moon would actually be more correct. Because it doesn't have an atmosphere, the light isn't going to refract as the sun comes into where the moon is. So, cool stuff there. So as we go from a lighter, a smaller index of refraction to a larger one, then we're going to bend towards the normal. My refracted angle is going to be less than my incident angle. The obverse here, obverse, is that correct? I don't know. The opposite is, okay, well, if we shine a light from the bottom here, so now light comes from the optically heavier substance. The N2 is larger than N1, okay? And then this is going to bend away from normal. So here's my angle 1, and so as we're going from N2 to N1 here, or rather, I guess in this particular case, if we were drawing the red, then this would be our new N1, because that's where my light is starting. And this is going to be my new N2 substance. And if we, again, if we assume that this is like air and water, okay, where we know that the water is always going to be larger index of refraction than the air, then as this light beam comes into the water-air interface, it's going to bend away from the normal. So my refracted angle is going to be less than my incident angle. And that only happens when we have going from a larger index to a smaller index. So in this case, N1 is larger than N2, so it bends away from the normal. And of course, our Snell's law will control and calculate what we have. Our angles will be in degrees, so make sure that your calculator is in degrees mode, not radians, for our Snell's law calculations. Okay, and then really the only other thing that we have to talk about here is the critical angle and total internal reflection, which is pretty cool. So if we take this last concept, going from a larger index to a smaller index, okay? And now, in both cases, as I increase my angle of incidence, my angle of refraction is going to increase as well. So that's going to swing out, and as I decrease, they're going to decrease. Same thing happens here. As I increase my angle of refraction, as I increase my angle of incidence, I'm going to increase my angle of refraction. As I decrease, they get smaller, okay? But it just so happens that when I increase my incident angle here as I'm going from a larger index to a smaller index, again, like from plastic to air, okay, then I can increase it enough to where my refracted angle is 90 degrees, okay? So, if I increase it enough, so this is what we call our critical angle, and that's when the refracted angle, our angle 2, is exactly 90 degrees. So the light actually goes along the surface, okay? And then if I were to increase it just a bit more, the light actually doesn't get refracted at all, but we call that total internal reflection, where if our incident angle is just slightly larger than the critical angle, it doesn't get refracted at all, but it gets totally internally reflected. Okay, so you can play a trick on your friends if you go swimming at a pool. Let's say it's a particularly large pool, like a city pool or something like that. Okay, and you are under the water. Okay, on the far side of the pool. Okay, you are hiding from your friends. Now your friends are over here, looking for you. Where are they? I don't know. I don't see them. Okay. Are they in the pool? Are they in the restroom? I don't know. Okay. Now we know that in order for us to see something, light has to bounce off the object and enter our eyes, right? Okay. So same thing happens here. The sunlight has to bounce off of you who are hiding, and enter the person who's trying to look at you. It has to go into their eyes, okay? But because we are so far away and we're just underneath the surface, all of these light beams that would actually get refracted out, because this angle is so big, it's going to be larger than the critical angle, and all of these light beams that reflect off of you get totally internally reflected. Is there a person at my door?
Yes.
Okay, so you are actually invisible to your friends. They literally cannot see you, okay, because the light beams are not going into the air.
What?
Biology. So Gallagher.
No clips from him. He has like a million of them, bro.
This quiz is new for last year, but Miss Gallagher is the IB teacher.
You can have ball, bro.
Yeah, you up?
Yes,
Now, this all changes as the observer, the person, your friend, walks around the side of the pool, and the angle that the light has to hit becomes less than the critical angle, and then, oh, they see you now. But this is just one example of total internal reflection. This is also how fiber optics work, where, let me show you, I can show you this thing here, so we get it real quick. So this is just a piece of clear plastic, acrylic, but it's in a tube. And I happen to have a nice bright green laser here, which you might have seen before. Where is it? Not sure how well this is going to work with the windows open, but if you can see, the green laser beam is bouncing inside of the plastic tube. But you don't see any green dots anywhere in the room, do you? No, because these light beams are hitting this plastic to air interface at an angle larger than the critical angle. Therefore, no refraction actually happens, but rather it's totally internally reflected, bounces all around inside, and then comes out kind of at the top. So you can see the green dot right there, but there's no green dots like if it comes out, it's going to look like that, but it doesn't. Cool stuff. All right. One more thing in terms of like applications, because you guys don't need me to do example problems. You guys are good in that, so I'm just going to leave that to you for your pods. All right. Unless you want an example problem. But what if, let's say we're on Survivor. Okay, Survivor. So we are out in the, like out on an island. There's no food. You gotta, catch your own food and stuff. But there's water, so there's fish there. And you're thinking, all right, I'm gonna, sharpen myself a spear, and I'm gonna catch myself a fish. Okay, because I'm hungry and I need to eat. All right. So here you are on the edge of the water, and you've got this spear. Okay, and you see a fish right there. Okay. Now again, we are assuming that light goes in a straight line. Okay. So if I throw the spear, and I practice, I got really good aim. I throw my spear, I hit my mark, but it doesn't hit the fish. Okay. The fish isn't actually there because the light beam has been refracted, because it has to go from the water into the air. So as it does that, so what I see is actually bent. The fish is actually a little lower than I think it is because of refraction. So if ever you're on Survivor and you're trying to spear hunt a fish, aim lower than what you actually see. There you go. Then when you win Survivor, just remember where you learned it. Okay. All right. Good. I think that's about it. Any questions for the good of the order? Yes. Can you go practice problem? Sure. Okay.
You have
I turned it in.
Oh, you good? So practice problem? I'm sorry, what? Okay.
Damn it. I don't have any boxes on my computer. I don't know how they're gonna let me.
Okay. Now notice
What's your computer?
for your pods, it's not the full set, but I only give you certain ones. And you know what? Let's just do one of them right now. Okay. So let's start with number 14. Yeah, 14. Let's do it right now.
What page is it on?
362 in your books. Alright, so your first pod problem,
262.
we'll do it as a class. It says a ray of light traveling in air was incident at an angle of 47 degrees to the surface of the plastic, which has a refractive index of 1.58. We are finding A, the angle of refraction in the plastic, and B, the speed of light in the plastic. Cool. Alright, so let's kind of draw it out here. So we've got air and we've got our plastic.
Yeah.
Okay.
Oh,
We
I
are
think
given
said
the
like-
plastic index is 1.58. Okay, 1.58. The index of air is just 1. We're going to assume, it's 1.000, something like that. But for all practical purposes, even down to 4 sig figs, it's just going to be 1. Okay? So we know that light is traveling 47 degrees to the surface. Now that's very interesting because whenever I talked about how we measure our angles are always measured according to the normal. Yeah, so they're trying to trick you here. They're trying to trick you by saying by the surface. So we got to do first a little bit of math so you guys can do it. So again, if this were like a real experiment, I would actually use a protractor and draw a 90 degree there, okay? So I know that the light comes in at 47 degrees to the surface, okay? So let's say that it comes in like that and the angle is 47 degrees, but the actual angle that I am looking for will be 43 degrees. this is going to be my angle 1 here. Again, measured with respect to the normal. Okay, now, what are we expecting as we're going from air to plastic as we go from a lesser index to a larger index?
Towards the normal?
It's going to bend towards the normal, giving me a smaller refracted angle. Good, okay? And then once we actually find that number, we can compare that to what we're expecting, and then we'll be good to go. All right, so I'm going to solve for my angle 2. That's the first part of our problem. All right, so of my Snell's law, I'm not talking about speeds just yet, but I do have my 2 indices. I've got one of my angles, I'm going to solve for my other angle. So I'm just going to ignore my V2 over V1 side right here, and we're just going to solve for theta 2. So we're going to do our algebra, so sine angle 1 times n1 over n2 is equal to sine theta 2. Remember, to solve for the angle, we have to get rid of the sine by taking the arc sine. In your calculator, that's the sine to the minus 1 power, but it is not the same as inverse sine. We talked about that last year. So as we take the arc sine, we have to take the arc sine of everything on this side. And unfortunately, no, it does not cancel out this guy. That still has to be in there because there's more to it. So I just got to calculate the whole thing. So when I do, let's see here. Using my calculadora, again in degrees mode, make sure that you're in degrees mode. So we got the arc sine, no, second. There we go, all right. So arc sine, let's see, n1 is 1, divided by n2, 1.58, times, let's see, sine of 43 degrees. Close that bad boy out. And I got 32 degrees.
I love my calculator.
Right. So, can you confirm my number? Because you really shouldn't take my word for it. You should check for it yourself. Because sometimes I make mistakes. Huh?
You definitely got 32.
What is it? So sine negative.
Which, I mean, technically this is less than my incident angle, right? So it matches what we're expecting. But make sure that I'm right. Check my math.
Oh shit, I'm supposed to be. Is it my turn yet?
I got 27.
Oh, I guess.
You got what?
27.
27.
Yeah,
I got
27. Are you
I didn't
in?
get that.
Hold on, can I see your calculator?
Guys, we're doing it wrong.
Yeah, make sure
You're
you're
already using the wrong angle.
Yeah, I got I thought it was degrees. You got about
Wait,
Yeah.
maybe.
Because that's the angle with the
Yeah,
first. And one is one. Yeah.
I just used the
So
equation
it
you
should
gave
be the arc sine
Yeah, can we use
of
it?
1 over 1.58
45.
times the sine of 43 degrees.
I got 25.6.
So do you,
I got 25.6. I got confirmed that it was 25.6.
This is why we check, y'all.
arc sine of 4.
Wait, make sure it's in degrees mode.
I
got mine. It's in degrees mode.
It's in degrees.
Sure.
Let me use my grapher because I might be typing stuff in.
Are we kidding?
I have it.
So when you
Times the sine of 45.
I see what you did there. That video.
Okay, yeah.
You
I don't know how I got that.
You good.
But
I wanted
it should be 26 degrees.
yeah.
Is that what you guys got? Yeah. Okay.
Well, he got 25.5.
I don't know what went wrong with
Round
my
up.
first
Yeah.
calculation. You're getting an error. Ooh, interesting. I'll have to check on that after I do the second part.
He said 26?
Yeah.
Okay, now.
The answer's
So that's
28.
part A. Part B is going to be a lot simpler. Finding the speed of light in the plastic. Remember, we had that equation that had the index of refraction is equal to c over v. So we're solving for the speed of light in the plastic, which should be less than 3 times 10 to the 8th meters per second, right? So using my math skills here, V equals C over N. So the speed of light in a vacuum, 3.8 times, I'm sorry, 3 times 10 to the 8th meters per second. Remember, this is a constant. It is found in your constants page in your IB booklet. Divided by the index of refraction, which was the 1.58, and we should get, well, it's really just, if we just do 3 divided by 1.58, and we can still keep the times 10 to the 8th power. So that's going to be 1.9,
0.
yes, with 3 sig figs. 1.90 times 10 to the 8th meters per second. That should be the speed of light in that plastic. Yes,
For part A, on the answer key it says 28.
28.
I got 25.5.
I got 25.
Well, that is weird. I wonder if we use the 47 instead, what would we get?
I got.
Opposite angle. That's what I should do.
27.5.
Yeah, so
So
it's
the
20.
key is wrong.
Oh, the key's wrong.
Oh, really?
Yes.
What?
Well, I mean,
The wrong
if
angle.
I look at the problem, it says the angle to the surface. But we always measure the angle with respect to the normal. So the person who made the key forgot
Not
that
a
it
physics
was the
wizard
surface
like
angle and
Mr.
not the
Bean.
normal angle.
That's why I said I trust Mr. Bean.
Yeah, so
Wait,
even though books are supposed to be perfect,
Mr. Main is more perfect.
they are not. Well, I'm not either, but there's no doubt that I'm right here.
No word, my boss.
Sometimes I can put it out there, but there we go. All right, guys. So that's about it. So the rest of it is just practice with those equations. So feel free to take 5, and then we can spend the rest of our class time working on our pods. There is a quiz for today. And then we are jumping into diffraction stuff for
Hey,
next
for
class.
that one, you know how
Yeah.
it says N equals C over V?
Yes.
Shouldn't the second part be
Aiden,
V
did you
equals C
still
times
need
N?
me to check your?
So when you
Okay.
so you would multiply by the b on this side
Yep.
and divide by the
There we
n.
go.
So you get
No, okay.
Well, so you just
so if you were to do it like with math, so you would do so you have n equals cv, multiply by v, then you have vn equals c, then you gotta divide by n, so then you have v equals c.
oh, I see.
Whoever made this book, is a genius. So it's 14.
Where did he get? He got 3 times 10 to the 8 from what equation?
3 times 8.
3 times 10
it's
to
a
the 8.
constant.
Yeah, that's what it was. I knew it was some sort of constant.
And then it's like 300 million meters per second.
Alright, let's do pods. Wait, Loki? Does he fix the quiz? Shit.
I can.
Let's see if this person lives, huh?
You're gonna visit
Check your class.
No, I'm gonna put on Google Maps.
Put it on Zillow, see how much the house costs. And then we gotta find if they're behind the house payments and then buy their house from the city for cheap.
See if they're getting evicted. If they own. Alright, let's see. What's this one? What's this one? What's this one? Alright. 8370 Boulevard.
It's my timer. It's just not attached to my screen.
8370. What was it? Watermill?
Watermill.
BLVD.
Oh,
Oh, oh, they're rich. 4 beds.
21, 22 people.
No, we're finding anything about everything about
Oh,
them.
was this built in
2004, yeah.
It's made of like brick too.
Let's see how long it took them to get to the school.